title of our talk is Preventing Readmissions Due to Sepsis with Wearable Monitoring and Deep Learning. We have from Patch Medical, Wei-Jien to talk to us about that. We got about an hour, so we'll have about a 45-minute presentation. If you have any questions, there's the Brella app, there's the More area, where for Hub 2, you could share your questions, pull them up in Slido, or I'll pass around the mic afterwards. But let's give a round of applause for Wei-Jien.
Okay, I'll make sure that works. All right. Thanks for showing up today, guys. This is kind of exciting. It'll be a nice opportunity to talk to you all. Now I'll stand on this side. Sorry, not ignoring you guys, but there's a few more people over here. Hi, welcome. So yeah, as David mentioned, my talk is preventing readmissions due to sepsis. It's a topic that's close to my heart and keeps me busy at the moment. It's all about the potential of using, machine learning, in this case, deep learning, to improve the diagnosis and triage of patients. So let's get. Okay. So just a little bit about me. So Patch Medical is a startup based in San Francisco. I am the CTO and co-founder. Kind of what set us on this journey is the fact that our CEO and my co-founder, he had a liver transplant 7 years ago. And as a result of that, because of some of the medications he was on and some surgical complications, he actually had 19 episodes of sepsis. So it's a very personal sort of problem that we're trying to solve here. When you consider that the rate of mortality for people that get sepsis is about 1 in 6, he's rolled that dice a few too many times. So we're out to automate the early detection of sepsis in at-home patients. So this is the key to what we do and where the wearables come in. And I'm here to share with you some of the work we've done with it. Really interested to hear your thoughts and feedback on it as well. For me, we have some problems which are pretty interesting sort of problems. So I'm sure many of you in the room have kind of encountered or worked with some of these problems. So would love to hear about you about that. So just briefly, a bit of housekeeping. This way this talk is structured is kind of in 3 parts. I'm just going to talk a little bit about what the problem is we're solving. Second is how we build a proof of data concept with EMR data, because that's readily available. And third is how we kind of think about transitioning this model to outside of hospital. And in the remaining time, there's some time for some questions or discussion if you guys have any sort of thoughts. All right. Those are rough times. We'll maybe or may not follow them. So first off, what problem are we actually solving? So you may or may not have heard about sepsis, but it is a big problem. Approximately 1.7 million cases of sepsis occur each year in the US. 270,000 of those result in mortalities. That's the 1 in 6. And if you look at the rates of mortality, sepsis actually kills more people than breast cancer, prostate cancer, lung cancer combined. So those are all conditions you may have heard of if you haven't heard of sepsis. So it's a pretty life-threatening sort of infection. Oh, well, not infection, but syndrome. And what is sepsis? Well, sepsis is a little bit tricky to define. In the last 30 years, there have been 3 different definitions of sepsis. But the way it's defined most recently is it's the life-threatening organ dysfunction caused by a dysregulated host response to infection. So put simply, what that means is that for patients that get an infection, what happens is their immune system overreacts to that infection. And can start leading to things like organ failure, shutdown, and septic shock. So I guess the reason why I brought this up actually is because it's quite relevant with some of the stuff that you're going to see later. The definitions of sepsis is actually how we label this data. So in some of the research that's out there, people have used some different definitions, so it is quite relevant. There are a lot of efforts to address sepsis. As I mentioned, it's an acute condition. What you'll find is that traditionally sepsis occurs in an in-hospital setting, or at least the way it's understood is that it occurs in an in-hospital setting. And critical care physicians will handle, or emergency department physicians will, triage patients and get them to the ICU if they're about to get sepsis. There's a lot of really great work going on in there, looking at things like time to antibiotics. The rate of mortality for a person once they get sepsis increases at 7% every hour. So that's compounding really, really quickly. So time is of the essence when we're dealing with sepsis. What's crazy about that, though, is that the CDC found that 80% of sepsis cases were already present when a patient arrives at the emergency room for treatment. So we think of a sepsis as an in-hospital critical care thing where we need to get them resuscitated on antibiotics ASAP, but for the majority of these patients, the beginnings of sepsis were there when they arrived. And this is kind of what problem we're trying to solve. What if we could identify in these patients that are outside of hospital that sepsis is starting to develop? If we could do that, what we could do is we can alert the treating team, who can then intervene earlier with things like prophylactic antibiotics or bringing the patient in for more testing. Either way, what it will allow us to do is prevent what is on average a $14,000 admission, which can be as much as $40,000 if the patient gets admitted to the ICU. Put something, we could put together a little system with patients wearing monitoring devices at home. That data would be connected to a mobile application which will allow us to get that data up to an analytics platform in the cloud, which would analyze this data and trigger an alert via phone, an SMS, a cascade to the clinical staff at a hospital. As a motivating example, I talked about my co-founder. On one of the episodes of sepsis he had, so this was after he had had it a couple of times, but he showed up to the emergency department and said, he had started to identify different signs of sepsis. What he had started to see was that he would get a warm face and sore legs, and it's a little bit different for different patients. But he showed up to the emergency department and said, "Hey, I think I'm about to get sepsis. I'm a liver transplant patient. I have all this medical history. Can I get admitted?" They took his vital signs. They measured his blood pressure, his heart rate, his temperature. They were normal when he was there, and so they told him to go home. They basically said, "We can't admit you. You look normal, at least from these measurements we're taking. So, see you later." Several hours later, he was back in hospital, and he was saying goodbye to his family. So, that's kind of like a motivating example for why we're doing what we're doing. Okay, so the first part of this talk is about how we built a proof of concept with EMR data and showed how we could apply machine learning to some of these vital signs. This is the end of the really nice, well-designed slides. Those previous slides I'd taken from my CEO for a presentation he'd done in Houston. So these are the slides I've put together and aren't as impressive, but the content's good. Okay, so the first thing we did was we kind of went out and started having a look at some of the literature and how people had been thinking about, identifying sepsis with machine learning in the past. If we look back at the literature, as early as 2002, people were looking at septic shock and neural networks, with rule-based systems. Of course, back in 2002, artificial intelligence and machine learning was still a fairly niche topic. And there was very little published between then and sort of 2015 and 2016, where we saw Suchi Saria come up with something called the True Score. She actually has a TED Talk about this, and a couple of other key papers that looked at using machine learning with a fairly small subset of data, although a lot of these other papers looked at as much data as they could grab from in hospital settings. So this is blood measurements, things like lactate, white blood cell count, nursing assessments, all these sorts of things that were being collected in hospital and were available in electronic medical records. Now, there was all this work out there in the field, but what none of these, or I guess what all these papers looked at was, hey, we've got an electronic medical record. What's all the data that we can stuff into this algorithm? But this wasn't really helpful for the fact that a lot of these measurements aren't actually available outside of hospital. So what we kind of decided to do was to take that EMR data, treat it as a time series classification problem, but only use physiological measurements that could be collected in an at-home setting. So this means things like respiration rate, blood pressure, heart rate, temperature, blood oxygen levels, that's it. But we could combine that with other factors that we know about this patient, things like their medical history, their demographic data, to build a model that would actually be, we could actually apply in an at-home setting. Next, we would label the data according to the latest Sepsis 3 definition. And of course, split the data into our development, validation, training sets to build our models. So this is kind of the general approach that gives an overview of what we were trying to do. Okay. So just kind of giving you a kind of look into some of the data that we were looking at. There is a typo on that slide. I put these slides together yesterday over lunch, so please forgive me. And a couple of things that we did find was that with these distributions, as we expected, for example, blood pressure, a decreased blood pressure was associated with the sepsis patients. An increased heart rate was associated with sepsis patients, and a increased respiratory rate was associated with sepsis. Now, if you have a look closely, though, we're talking about the medians there are off by maybe, 10 millimolars of mercury for the blood pressure, heart rates. It's also, very slightly above and below. So we're talking about slight differences here. We also looked at things like the variability of these variables, and an increased temperature variability was associated with sepsis. Plus, that was the major one. We also put together some inclusion and exclusion criteria. Obviously, we had access to 200,000 plus patients from a couple of ICUs, or a number of ICUs across the US. We decided to limit the scope of this analysis to adults only, actually pediatric and neonatal sepsis, so children's, presents a little bit differently to adults, and the majority of data that we had was in adults. Now, one of the challenges with dealing with electronic medical record data is that there's a lot of missingness and a lot of quirks to how stuff is recorded. In many of these medical record systems, things like microbiology cultures or blood cultures were really underreported. The reason for that is that in many cases, and this is what we're seeing with a data set that we're just about to get from Australia, is that the results of these blood cultures, for example, they're actually stored in a free text field. So it's really messy to try and get them out, especially when we're concerned with what time was this taken? What's the timestamp associated with that? What was the result with that? When did they get that result? So we excluded patients that were from medical record systems that had, underreported cultures. The reason why we underreported cultures actually is because this relates back to what the Sepsis 3 definition of sepsis is, and it's how we find it retrospectively. We also excluded stays if they had too few vital sign observations, effectively missing data. And we excluded patients who were labeled with the ICD code for severe sepsis, but did not meet Sepsis 3. So let me explain this really quickly for people who aren't that familiar. ICD codes are the billing codes associated with different procedures that happen in hospital and outpatient settings. So sometimes patients will get an ICD code for sepsis. Now you might say, great, let's use that as a label for sepsis. We know which patients got sepsis. Yes, we sort of do, but we don't know when they got sepsis. So putting a timestamp around that is a little trickier. That's where the Sepsis 3 criteria come in. Additionally, there's a couple of papers out there that look at like how well ICD codes represent sepsis, and it's not great because in many cases, sepsis is difficult to identify retrospectively for a coder. Also, there are slight incentives not to consider a patient septic because of the current requirements for reporting outcomes due to sepsis, which a lot of states have and is also required on a federal level through CMS. So they were discarded. In the end, we ended up with about 47,000 patients. Roughly 13,000 patients of those were septic. So there is a little bit of a class imbalance there, which is relevant later. And so this is not super important, but it's just an explanation of how we labeled the data and how we got a timestamp for when sepsis was about to occur. So from this Sepsis 3 definition, it defines sepsis as the time when there is it's the dysregulated host response to infection, if you remember. So how do we know that an infection occurred from the medical record? Well, if there was a blood culture and antibiotics administered within a certain time period, we could consider that a suspicion of infection. So standard of care generally is get them on fluids with antibiotics, take blood cultures, and you'll see what those results of that are in a day. So that tells us if there's an infection. Secondly is to look for whether there is an organ dysfunction about to occur. So what we look at for that is actually the something called the SOFA score, or the Sequential Organ Failure Assessment. And when that increased by 2, along with this suspicion of infection, there was a window around that, that's when we considered sepsis to have occurred. So this actually gives us a definition of sepsis that is more tied to the underlying physiology than just, whether a medical coder identified sepsis from the medical record. And in the end, this is kind of a rough, this is a histogram, not a histogram, a frequency table with just some of the distributions of demographics that we had in our patients. So it was a little skewed on the ethnicity. The age is a little bit, generally patients are much older, 60 or above, slightly skewed towards male as well. So we built our training set. The way we did this was we split this into sepsis positive and sepsis negative stays. So we are dealing with time series data here for all the vital signs that we get. And if you look at the stays, what we're interested is identifying sepsis before it occurs. So we discarded all the data from a sepsis day after that onset of sepsis. But if you do this, what happens is that it actually means that your sepsis stays are now, or your sequences are way shorter than your negative stays. So this is why I split them up into sepsis positive and sepsis negative. There was a little bit of a class imbalance, so we augmented some of the sepsis positive patients to boost their numbers. We adjusted the label, the time label, or time onset, there's timestamp there, by plus or minus a random number between 1 hour, just because there's a little bit of uncertainty with when exactly sepsis happened. Sepsis doesn't happen right at this minute or, right at this second. It's actually more of a syndrome that kind of appears over time. Then we sampled our sequences randomly from the sepsis negative stay. So we didn't want to bias, the start or the end of a stay where a patient might be a little bit healthier. And we split the data into mini batches and sub batches to decrease training time. This part's a little bit interesting. When we're thinking about development or the validation set, because we are dealing with a full patient stay or a time series, what we need to do is make sure to adjust for a couple of variables that will be different. So because we discarded all the data after the sepsis positive stay, like I mentioned, it's going to be a lot shorter than the sepsis negative stay. So if we were just to take the full sepsis negative stay, chuck that into our validation set, what you'd see is that all our sepsis negative stays would be much longer than the sepsis positive stays. And what you'd see is that this algorithm might actually start to learn on the length of stay as opposed to just what it's seeing in the moment. So, once you're like, oh, most sepsis happened within, the first 8 to 10 hours of being in the ICU. If you're making a prediction at 2 days after being there, it will be biased towards predicting negative. And because there was a little bit of a class imbalance, what we did was we matched up sepsis negative stays to a sepsis positive stay and sampled a length of data that was equivalent to that sepsis positive stay. So I'm hoping that's clear from this data, but the gray parts are the parts we discard, the white parts are the actual stay that we want to take. And for each matched group, the sepsis negative sequence should be about the same as should be exactly the same as the sepsis positive sequence. Any questions so far? Cool.
Yeah, sorry.
Oh, yes.
You mentioned you augmented the sepsis positive data.
Correct, yes.
What type of augmentation? Was it synthetic or?
Well, it was not synthetic in the sense that we didn't create new samples. It wasn't like randomly generated. What we did was we would take the sepsis patient. We would adjust the onset of sepsis by a random amount, and we would also swap the order of some of those measurements. So if they occurred at the same time, we would swap the order of them, for example. So shuffled them. So you'd get the same values, but within the same amount of time, but it would be just slightly different ordered. So building the model, I guess we decided to use LSTM networks due to their high performance. There was a lot of really good papers out there that were showing, great performance. We're also, I guess, curious to see, how that would go. We use TensorFlow to build our models. The way we actually rolled it out, because we were running a lot of experiments in parallel and there were a lot of hyperparameters. There was a big hyperparameter space that we wanted to sort of cover, was we Dockerized or containerized how we ran the experiment. So it was really easy to run that on multiple different cloud instances at once. And we trained the model using a bunch of GPU P2 instances on AWS. So for the physicians in the room, those are great for running neural networks, those GPUs. So the rough model ended up looking like this. We had normalized input vectors with some demographic information. I should say medical history as well. These various measurements. We fed that into an LSTM network to pull out some of the time dependencies. And we followed that up with just, a standard dense layer neural network after, which spat out a prediction. So it wasn't too crazy, but it did mean that we had, a fair amount of hyperparameters to optimize for. So this part is actually something that's I think is actually kind of cool. So obviously there's a really big parameter space that we had to cover, because of all these networks. The issue is that picking one performance metric for what we're doing is actually it isn't a great idea, because if you pick a single performance metric, what you end up optimizing for is that particular performance metric, and it doesn't necessarily represent what you're going to see in the real world, or how, as some of the talks talked about yesterday, a lot of publishing companies and researchers end up trying to maximize the area under the curve. That becomes that single number that they're trying to hit, and then they can brag about. But actually, it might be falling back on positive predictive value or something else like that. So we wanted to optimize this network without just a single parameter. So how we did it was we actually combined a little bit of human intuition, because HI, that human intelligence, is pretty good still. So what we did is we did a coarse grid search to establish, a reasonable set of starting hyperparameters. Then we would begin a random search from there. We would take the old experiment and the new experiment. We would run the two experiments for 300 epochs or so, and we would then present the metrics to a human. Obviously now this seems like a really time-consuming process. So what we did was we actually set up a Slack bot with a little channel where it would just say, hey, this experiment ran, these are the metrics, which one do you think is better? So we would pick old, new, and depending on which one is better, we would save that set of hyperparameters, and we would then do a random vector in a new direction, and run a new experiment. So in this way, it would converge to a good set of hyperparameters. So in this example, we have the area under the receiver operating curve, area under the precision recall curve, which is what we started off with. We've since added a couple of other parameters as well, but this is kind of a cool little thing we set up to handle this process. So yeah, on validation, this is actually missing a couple of points, but we naturally everyone talks about the area under receiver operating characteristic. We were also quite interested in the precision recall curve because there was a little bit of a class imbalance. We did actually look at, sorry guys, I didn't have the numbers for positive predictive value, but that was roughly 0.7 when we selected a threshold. What we're trying to optimize for, when you think about it, at least our intuition is right now, is that we want to minimize the number of false positives because we're an early triage system. What we're interested in is making sure that physicians trust what we do. There's physician burnout, there's alert fatigue. So what matters is that when we say that someone's about to sepsis, we're pretty confident that's going to happen. So here's a graph. This is the receiver operating characteristic. The blue in the top left corner is at onset. So typically, when you think about, area under the curve and that sort of thing, you think about it at a time point, which makes sense in terms of a diagnostic blood test. Maybe you have a blood test and you take a test and you go, okay, does this patient have this disease or does it not? Because we're actually a real-time monitoring system, we're actually doing that analysis, or that analysis like multiple times at all these different timestamps. So we have to think about the performance metrics a little bit differently. But anyway, at onset, 0 hours, we're a fair bit better than Muse, SOFA, Q-SOFA, SEERS. What they are some standard of care risk scores that are used in hospital. They stand for the Modified Early Warning Score. Q-SOFA is the Quick Sequential Organ SOFA score. That's something that was talked about in the latest definitions of sepsis as well. So if you look at the green line, that's if you go back 8 hours and we predict, we were still, slightly better than these risk scores. So this is a similar graph, but with the precision recall curves. So we could get, and recall is sensitivity, precision is positive predictive value, just to make that clear. Although we talk about precision recall, so I don't want to confuse anyone. So at a sensitivity of 0.5, we could get a positive predictive value or precision of about 0.7. And this is kind of a little bit more results just over time. So really, we're interested at understanding the performance of this algorithm at multiple time points. So if you go right out to the end, that's 8 hours before sepsis. You can see the performance does drop off a little bit over time. All right. So then that begs the question. So that was obviously done on electronic medical record data. We're interested in preventing sepsis at home. You might think, well, that's a really different setting. That sample is not very representative of your target population. You are kind of right. Unfortunately, there doesn't exist, well, at least not to my knowledge, and we've spent a lot of time looking, a big ambulatory data set, so that's at-home data with all the measurements that we want to find, plus the fact that it would be tied back to a medical record so we could label our samples. So how do we do that? Well, that was the starting point. That was like, hey, here's some proof that we can build a model, that it works. We can use just vital signs that are available in an at-home setting. And we can beat some of the current risk scores. The bar wasn't very high, let's be honest. And in hospital, there's a lot more diagnostic tools that, there's nurse assessments and all that sort of thing. But, it still wasn't a very high bar to beat. So we asked ourselves, what's the difference between this in-hospital data and this out-of-hospital data? Well, for one, there's a lower incidence when it comes to the rates of sepsis. Secondly, patient compliance results in missingness of data. So if patients have wearable devices, they're only so good insofar as they wear the devices. Not just wear the device, but when they're moving, we do get movement artifacts, which does affect some of the quality of the data that we get or the availability of data. And just little logistical things like device batteries go flat, right? So what happens when we lose that data? So this is a general approach about how we're thinking about this. We did that ICU proof of concept. We're getting a different set of data from patients that are slightly less sick, which is the general ward, and we're also getting data from the at-home patient. So we're going to be running a prospective observational study to collect some of this data so that we can test the models that we built and see how well they translate to an outpatient setting. Because remember, the underlying physiology is fairly similar, although there are differences there. Yeah, so this is an example of some heart rate data that we pulled off one of our devices or the monitoring patch that we have. As you can see, there are points where there are blatantly missing data. So this data is after it's been filtered for data that was affected by movement or sort of the poor positioning of the patch. So as you can see, there are several hour blocks there which are missing data. Too far. So how do we collect the data? Well, there's a number of wearable devices that we can use. You're probably thinking wearables, that's Apple Watch, Fitbit, Samsung's smartwatch, right? Yeah, those are definitely some options. They're consumer grade. They're generally consumer grade, considered consumer grade. Although the Apple Watch is FDA cleared to identify arrhythmias. That said, it only takes a point-in-time ECG. However, there are also medical grade options. Now, these medical grade options, they're generally FDA cleared. What that means, to get FDA clearance, I guess the big difference in why they cost so goddamn much compared to these consumer wearables is that when you're developing a medical device, you need to design that thing to certain engineering standards, and then you need to show it with testing, and then you need to document that with testing. So you need something called a quality management system, which outlines, we made this design decision, we did this testing, here's all the documentation to show it. So it takes a lot longer to develop these devices, and you develop to, tighter tolerances. That's basically the fundamental difference. So which ones did we pick? Well, we went with the FDA cleared devices. Fundamentally, they're validated for accuracy and safety. Your Apple Watch isn't going to kill you, but it's still not necessarily developed to the same sort of standards. The FDA, the way they regulate machine learning algorithms now and software as a medical device is actually, they're very concerned about the quality of data. So having FDA cleared devices is actually, something that they'd much prefer. So combined, we measure systolic blood pressure, diastolic blood pressure, respiratory rate, heart rate, skin temperature, and SpO2. And each of these devices have onboard memory to collect data. So, if they're in a place where they can't stream immediately, we're still collecting that data. And there's various data quality metrics which we can look at to know what data is actually valuable and which ones we can discard. So, how do we collect the data that we need? Well, this is a fairly new field of research. I would say ambulatory monitoring is not 100% new, but the amount of data that's been collected is still very limited in ways that have been applied to fairly small sample sizes. It is expensive to collect this data. As I mentioned earlier, there's no ambulatory monitoring databases, and prospective data collection is expensive. So what are we doing? We're doing a staged data collection exercise actually in high-risk patients. So certain patients are at higher risk of getting sepsis. Patients that have had chemotherapy, for example, people with blood cancers, leukemias, solid organ tumors. These patients, we know, have an increased risk of sepsis that is tied to a defined event. So wearables are not at the stage yet where a patient wants to wear a monitoring watch and a monitoring patch 365 days a year. So really we want to get them at periods of heightened risk. So we're running up some pilot studies as well with just our monitoring, with a nurse monitoring for deterioration to collect data. So there's double-pronged approach to this. One is we run our prospective studies with some research hospitals, and secondly is to run pilot studies with less research-focused hospitals where we can monitor their patients for deterioration, but we can also collect that data. And then what are we going to do with that? Well, we can then characterize some of the missingness of data. We're looking at metrics like, that should be not rate, but it should be ratio. The number of hour bins with missing values relative to the number of bins that have usable values. So when we're building our EMR algorithm, we were receiving data, roughly every 45 minutes. There were measurements taken roughly every 45 minutes. So really what we need to do is at least have one measurement for every 45 minutes. We do interpolate as well between some of those times. We've been doing a mixture of forward filling and linear interpolation. They perform roughly similarly in terms of performance, although linear interpolation does have an issue with the fact that sometimes your heart rate's really high because there's a stressful event, or you spend a lot of time walking or exercising, And so if you interpolate between that, it doesn't really make sense because that's a spike, not a gradual increase. Then we're going to retrain the data with the hospital ward setting with some of this missingness simulated in at-home conditions. So what we've done so far is we've kind of simulated missingness of data with just randomly dropping out measurements from that time series. However, this isn't necessarily what happens in the real world. It's not necessarily random. You lose data at certain points. So that's what we're characterizing that. And secondly is obviously collect data from the at-home setting. Sorry, typo guys. Collect data in an at-home setting. As I mentioned, this is from prospective and observational study. Okay. To summarize, wearable devices offer a really amazing opportunity to monitor high-risk patients when they're being discharged after an inpatient procedure or an outpatient procedure. We know that 80% of sepsis occurs or is present when a patient shows up to the emergency department. We also know that with a reduced set of physiological measurements and some deep learning models, we can predict the onset of sepsis better than some existing risk scores that are used in hospital. And with a combination of data sources, so by combining our ICU data with this ward data and at-home data, we can actually retrain this model to hopefully apply out in an at-home setting. And so we're collecting that data where we can actually validate that, in an at-home setting. Yeah, so that's kind of pretty much an overview of how we're approaching this and how we're thinking about the topic of at-home sepsis detection. So currently, the things that we do have in progress are this ward study. I actually would have liked to show you some of that data today, but we're a little bit behind on that one. And I'd love to come back and, I hope I can talk to you guys at some point as well about when we do have that at-home data and to show you what that looks like and how it applies. So now, I think we've got a little bit of time for questions.
Excellent. So round of applause for Wei-Jien, Patch Medical. And feel free to raise your hand. I'll head around with the mic.
A quick question. From how much time did it take you from collecting the data, data cleansing, structuring, and building the model till you validated it? How much time did it take your team to do that?
That's a good question. So a lot of the things so to get sort of some initial results, it was probably 4 or 5 months in total. But what we did find is that actually there's a lot of peculiarities about dealing with time series data and time series patient data. So some of the things like how we set up that validation set and how we adjust for things like the length of sequence, that was stuff that we only figured out a little bit later. So after we'd done the initial thing, and then we had to go back and then rerun things with those sorts of different assumptions basically tested. So that added another extra couple months on top of that. Yeah.
Thank you for the detailed explanations. For the comparison with the source criteria, you showed a huge difference in the area and the curve and the precisions. Is there any specific features that is different from source? And one more thing is did you consider the bimodal distribution of the temperatures in source criteria in this model? Because the temperature can be high
or low. Yeah. So that, when we compared against SIRS, that's we did consider the high-low temperature for that model. We also, so the inputs to that are white blood cell count, which is something that we can't measure in an at-home setting, so we left that out of our model. The explanation for why it didn't perform so well, I'd suggest that's probably, SEERS tells you about inflammatory response, but it doesn't tell you about the infection that's happening. I suspect that's probably missing some information into some there. You know, it does have temperature, but fever is, you know, it's a blunt tool, yeah.
I have a few questions.
Mm-hmm.
So for the data you use for training the model, is that from the ICU EMRs?
Yes.
So how often like you get this data and label this non-sepsis or sepsis?
Yeah, so we were getting measurements at roughly, on average, every 45 minutes.
Every 45 minutes. So you can simulate at home as 45 minutes.
Yes,
But
yes.
except for the difference of the, like, if there's missing data at home, so
Mm-hmm.
do you think like the environment changed, like the patient maybe like have totally different activities at home rather than in the ICU, so they just lay on the bed for the most of the time, but at home probably like active more. So I see the very slightly different between the sepsis and non-sepsis within the like the blood pressure, the heart rate, or the temperature, or the other features. But if something just slightly changed at home, do you think that would be a huge effect for your models?
Yeah, so we're actually collecting data also from the general hospital ward where patients are able to get up and move around. So that does exist in medical records as well. So I think to your answer, yes, it'll have a little bit of an effect. We're not 100% sure how big or small that's going to be yet. But by diversifying the source of data that we use to train on, so ICU plus ward plus some at-home data, obviously that's going to be a lot smaller in the amount of that we have. But we're hoping that will account for some of those little differences.
So you're measuring different physiologic measurements, right? Vital signs, temperature, blood pressure. How do you decide which one has the more impact? Do you give them the same impact, or how do you decide which one has the higher impact than predicting sepsis?
Yeah, that's a good question. So the way we approached it is we basically fed them in raw as a raw series. We didn't do a whole lot of feature engineering. The reason for that is, well, I shouldn't say that. We did do a little bit of feature engineering with a logistic regression model early on, but we looked at the finite differences between successive measurements. They actually showed a small or a very weak sort of strength in terms of features relative to just the raw data. Actually, from the literature, it seems that it's the way multiple vital signs correlate that's actually more interesting or more predictive of sepsis. But that was kind of, we didn't specifically look at that. We did look at individual features and did some feature analysis by dropping out different just like a blunt force drop out a particular vital sign. And what we did find was that actually SpO2 was particularly important. But if you saw the distributions there, the distributions looked very, very similar between sepsis and non-sepsis patients. So there's actually some second order correlations there that are being learned by the network. Yeah.
Hi, quick question. So you mentioned earlier in the optimizing the performance, you actually wanted to lower the false positive.
Yes.
Did you do that at the expense of suffering with the sensitivity?
Yeah, so when we're selecting the thresholds, that is a little bit of a trade-off that occurs. That's a little bit unfortunate and unavoidable. But from that initial model, the sensitivity, at a positive predictive value of about 70%, it was 50% sensitivity. To give you some context, that may seem low, but when we consider what the standard of care is for a patient outside of a hospital, it's nothing. It doesn't exist. So yes, we are going to miss patients, but if we miss them, what's going to happen is that they're going to end up in the normal channels. Basically, they're going to show up to hospital and be stuck with the same issues with maybe they don't get admitted. But if we can capture just a small amount of patients, well, it's still an improvement, above zero. So
So you think it's actually costlier to admit someone who doesn't have sepsis versus losing someone who has sepsis in terms of healthcare?
Costly to admit someone who does not have sepsis, so a false positive, as opposed to yes, to an extent. So there's a couple of competing factors here. It's not just a simple does the patient show up or not show up. It's also the fact that physician buy-in and clinician adoption is also a competing factor. So that also is a factor which if we're sending a bunch of alerts, they're going to ignore them. So that in itself is an optimization problem. Yeah.
Yeah, hi, excellent talk. So, so I see these patients all the time. I think this timely recognition at home is absolutely, the big gap in our care. One of the other things that I think could potentially be used is, so these are the patients when they get admitted. Early discharge is also a big gap in care that we always struggle, and I could potentially see application of wearable devices, for example, for somebody who comes in with potential sepsis or who's otherwise doing well and could potentially go home on IV antibiotics even at home. Yeah. So that's one set of patients that certainly could be used. I guess one of the questions that we always have is the variables that you're looking at, like the heart rate and pulse ox and everything else. Heart rate is so dependent on so many other factors. All our patients are anemic and their heart rate is always way above the normal range, and our ranges are so different. So how do you then sort of standardize that a very important variable that is going to determine the outcome? Yeah,
so that's a really good question, and you're right in that vital signs in themselves do lack a certain specificity, and it's hard to separate the confounding factors and the noise. I guess the way we're thinking about this is that we're actually looking at a lot more variables than just heart rate. So if we were purely looking at heart rate, yes, we wouldn't know if it was because that patient was just about to get up on stage and do a performance or something like that. With the literature for sepsis, it's actually how the heart rate and respiration rate and blood oxygen concentration vary with time. There's a rhythmic pattern to how they vary. So because we're looking at other variables, and we're also looking at the patient's medical history and demographics, there's a lot more information there that helps to sort of pass signal from the noise.
Okay, I'll take one more question.
Yeah. Hi, thanks for the presentation. So I have two questions. One is, I think you used this is more like a detection for the sepsis symptoms. So I'm just wondering how, for regular consumers, how do they know they have the potential of growing into the symptom, comparing to what you mentioned here as Apple Watch or Fitbit and other smartwatch, where people just can buy regularly instead of buy a patch, adhere to them all the time. I think that's one thing, and the other is for the other parameters. Like temperature and heart rate, how do you roll out all the aggressors in terms of, for example, just room temperature, or they just went to a very hot place, and for example, they're working out, their heart rate just jumped, things like that? Thanks.
Yeah, so on your first question, I think that the general consumer shouldn't think about trying to identify if they're going to have sepsis. If you're healthy, you're probably at a low risk of getting sepsis. What happens is you might get a cut, you'll get an infection. Hopefully you put some antibiotic cream there and you cover it up, and you'll be fine. Your immune system will deal with that and you'll be A-okay. Sepsis is particularly, I guess the incidence rates for a healthy person are very, very low. Now, if you are immunocompromised because you're on certain medications, or you had chemotherapy, which wipes out your immune system, then you're at a higher risk of getting sepsis. So this is why we're focused on treating this as a medical condition as opposed to just a general wellness condition. To your second point about temperature and dealing with, some of those signals, that's actually one of the things we're characterizing right now. Is we're looking at how temperature varies with different room temperatures and different sort of like skin conductances as well. But what we do have with the data that we're collecting is that we have a time series over a long period of time. So we can get basically like a moving average, if you will, of what we would expect that to be, right? So there's a certain we know what we expect it to be versus what we actually measure. So there is a certain bit of noise filtering that we have to do there. Maybe we want to talk afterwards. I can go into a bit more detail about that.
Great. Well, let's give a round of applause again for Wei-Jien from Patch Medical.
Thank you, guys.
Feel free to stick around for a few more questions. Our next talk will be in about 5 minutes.